Hello, dear students. I welcome you all in this statistical mechanics class. So, in this today's lecture, we will discuss about the density operator, and then we will derive the expression of this quantum mechanical ensemble theory, in which we will prove this quantum analog of this Lively's theorem, which we have already derived in our unit number 1, and that is the classical version of this Lively's theorem. So let us start our lecture. So before going to explain the basic concept of a density matrix, so I would like to explain about first the symmetric and antisymmetric wave functions. Antisymmetric wave function. So in our yesterday's lecture, we have discussed about the quantum mechanics of this Schrödinger wave equation. So for this n-identical particle, our Schrödinger wave equation, so that is our Hamiltonian energy function. So psi, that is our wave function. So it is equal to IH bar curly psi by curly t. So this psi, which is a function of position and time. So each of these number of particles, so they are representing the position and spin of these particles. So here the Hamiltonian H function is symmetric in its argument due to the identity of these particles, because we generally consider that the particles are identical in quantum. So the identity of particles, which means that they can be substituted for each other without changing H or any other observable quantities. Now there are two kinds of solutions of a wave function, and first is symmetric wave function, so which we generally represented with psi s. So a wave function is said to be symmetric if the interchange of any pair of particles among its arguments leaves the wave function unchanged. So second is antisymmetric, so which is generally represented with the psi a. So in this a wave function, it is said to be antisymmetric if the interchange of any particles or any pair of particles among its arguments or among the operator, it changes the sign of this wave function. So in symmetric, it does not change any sign of the wave function, while in antisymmetric, when the wave function act upon by this operator, so it changes its sign. So here I would like to tell that the symmetric character of a wave function does not change with the time. Now if psi s is symmetric at a particular time t, then if I write h, which is our operator, so h psi s, it is also symmetric, and according to equation 1 curly psi s over curly t, so it is symmetric with time. And similarly, if psi a, it is antisymmetric, so at any time t, and if we are acting operator h, and therefore h psi a and curly psi a over curly t, so they are antisymmetric. And the integration of this psi a, it also shows that it is antisymmetric. So how we can represent these two types of wave function? So if P is any exchange operator, so as I have discussed that it can be a differentiation operator, it can be an energy operator, it can be an integration operator. So when this operator act upon this wave function, so it remains symmetric. So with although it changes its position, but it does not change its sign. So similarly, this operator when act upon this antisymmetric wave function, so it changes its sign. So this is antisymmetric and this is symmetric wave function. So the identical particle having an integral spin quantum number, they are generally represented with the symmetric wave function. So the class of particle like the particle which describe the symmetric wave function, they are generally known as bosons. So all those particles which is having integral spin, so they are generally comes in the category of symmetric wave function, and so they obey Bose-Einstein statistics. So the examples of boson, you know, that is photons, neutral helium atom in normal state, so and so. So similarly, on the other side, the identical particle having half or odd integral quantum number, they are generally known as antisymmetric wave function. So they comes in the category of fermions. So all those fermions, they are showing antisymmetric wave function characteristics. So the particles, so these type of particles, they show obey FD statistics. And examples of fermions, you know, that is electron, proton, neutron. So they are fermions having half integral spin. So this is all about the symmetric and antisymmetric wave function. So therefore, from this, the average value of any dynamical physical quantity, so phi if it is in the state psi, so it is generally given as integration of psi star psi. So if P is the operator into d tau over psi star psi into d tau. So here P is the operator which is corresponding to this dynamical physical quantity small p. So this is small p. So the operator which is associated with energy, so that is generally written as I h bar curly over curly t, and the operator which is associated with the momentum, so that is generally written as h bar over I into del, so that is minus of I h curly over curly x, you can write. So if psi is the normalized function, so then we can write this integration of psi star psi d tau, that is equal to 1. So therefore our this expectation value of this p dynamical quantities, we can write it psi star p psi into d tau. And it's a symmetric and antisymmetric wave function, we can write something like psi s star p into psi s into d tau, and its antisymmetric wave function, that is psi a star p into psi into so d2. So next is density matrix. So before explaining this, you should have the idea about the statistical weight or the theory of equal a prior probability. Now, in most of these statistical particle distribution, so there is only one eigenfunction which corresponding to each eigenvalue. Now, in such cases, eigenstate of the energy level it is said to be non-degenerate. However, in some other cases, so there are number of eigenfunctions which are corresponding to a single eigenvalue. So that state or that eigenstate it is known as the degenerate eigenstate. So in the degenerate cases, the number of the number of eigenstates for the particular energy state or level you can say, so it is called the degeneracy of that state. So if Gi it is generally represented with this degeneracy for these eigenvalues, so we generally represents these eigenvalues, energy eigenvalues as Ei. So then Gi is the number of eigenstates. So these are number of eigenstates for the ith eigenstate which is having energy, so Ei. So this is the energy of ith eigenstate. So for non-degenerate, since we know there is only one eigenvalue, so therefore for the non-degenerate state case Gi is equal to 1. So the important postulate of quantum mechanics which is concerning about the probability of these eigenstate, so which generally possess the theory of an equal a prior probability. So what does it mean? So in quantum statistics it is equivalent the eigenstate it is equivalent to unit cell in the phase space. So like we consider the particle which is in as the unit cell in the phase space. So in quantum statistics we generally call that phase space cell as the eigenstate. So therefore the degeneracy Gi, so it is often referred to as the prior probability or the statistics of the given eigenstate. So this is generally known as the statistical weight in quantum mechanics. So now a pure quantum state of a system it is represented by a single eigenvector. So if we have a wave function, then we generally represent this single eigenvector alpha. So if we have these many other eigenvectors which are having this statistical approach, so we can write this pure classical state as Q1, so which is having position coordinate, so up to Qf, and momentum coordinates as P1, P2, Pf at each instant of time. And the statistical state it can be described as a function so which is dependent upon these position and momentum coordinates, and it is dependent upon a time function t. Therefore the probability that a system it is found in these interval dp1 uh, dq1 dqf dpf at time t. So that is generally represented with this density function, so which is a function of dq1 to dqf, a momentum function dp1 dpf, and a function of time t. So the quantum analog of this classical density function, it is generally known as the density operator, and its representation in the matrix, it is written, or it is explained in the form of a density matrix. So the density, classical density function, which we have described in this classical statistics, so that is equivalent to density matrix in classical statistics. So let us solve this quantum mechanical ensemble theory to derive the expression of this density matrix. Now consider an ensemble of n identical systems. So we have a ensemble which is having n identical systems, and this n, it is very large in number. Now these systems, they are characterized by a energy function, so that is generally known as h operator, that is the Hamiltonian function h. Now let psi k rt, it describes the normalized wave function. So which describe the physical states of the kth system. So this psi k, it represents the kth state of the ensemble at time t. So this k, it can be any number, 1 2 up to the order of n. So n is the total number of systems which are present in this ensemble. Now the time variation wave function, so of the Schrodinger wave equation, so we can write the time variation function of this psi kt. So that is equal to h cap psi kt. So if I apply this energy operator to this wave function, so this equation becomes I h bar curly psi k over curly t. So this I can write also as I h bar psi dot. So this dot, that is representing curly psi over curly t. So let us say this is our equation number 1. Now if I introduce a complete set of orthonormal functions, so that is phi n. So what are these phi n? So these are the different wave functions at different time t. So and I apply this operator to this orthonormal function. So this is equal to en into phi n. So this wave function psi kt, so that is the total wave function. So it can be write as the linear combination. So this psi kt I can write, so that is equal to summation of a n kt into phi n. So where a n kt, that is generally known as the probability amplitude of this wave function. So a n kt, so let us say this is our equation number 2, and this a n kt, so that is phi n star psi kt into delta tau. So this is equation number 3. So here phi n star, that is the complex conjugate of function phi n. and delta tau, that is the volume element in this coordinate surface, that is the characterized volume. Now, before driving out this expression for this psi kt, so we need to find out the value of this a and kt. So a and kt, so they is the coefficient which represent the probability amplitude. So this a and kt represents the probability amplitude for the various systems, so which can be in any state, so of the ensemble to be in various states. So states we generally represented with this phi n. So the physical state of this kth system, it can be described equally well in terms of this a and kt. So therefore this time variation of this probability amplitude we can write down as I h bar a n k of t. So this dot represent, it is a derivative of uh, curly a n k over curly t. So this we can write as I h integration of this, putting the value of a n k t. So that is phi n star psi dot kt into delta tau. So phi k dot, so this value which we have discussed in this equation, so from this equation number 1 we can find out the value of this psi dot kt, so that is equal to 1 over h. So psi dot kt, so which is equal to 1 over I h cap psi of kt. So putting the value of this psi dot kt, so in this equation, so this equation becomes I h bar a n dot k of t, so that is equal to I h phi n star 1 over I h bar h star into psi of kt into delta tau. So this get cancelled with this. So what we are left with is phi n star h operator psi kt into delta tau. Now putting the value of this psi kt in terms of this probability amplitude and this system states, so this equation becomes, so I h cap a n dot of kt, that is equal to phi n star h, so psi kt, that is equal to summation of amkt. So that is for any other states. Suppose that state, system state is represented with as the mth state. So this becomes amkt into phi of m into delta of tau. So this becomes phi n star h of phi m delta tau into am of kt. So this integration and this function, that is generally written as the Hermitian operator. So that is n m Hermitian operator into probability amplitude. So integration, it turns into this summation. So here phi n star h cap dm into this phi m into delta tau, that is generally written as this Hermitian operator nmm. So therefore now this psi of kt we can generally represent, so that is showing the total probability amplitude. So this we can write as amplitude for the first state phi 1 for first particle. So similarly for the kth state for the second particle phi 2, so and so, so up to the order of a n k up to phi n. So therefore this ANKT square, so that represents the probability that a measurement at time t find this kth state of the ensemble to be in particular state phi n. So this we generally represent as the probability of measurement of the kth system to be in state phi n at time t. So therefore the value of this probability amplitude a n k of t square, that is equal to 1. So this is for all these states which is representing k. Now we introduce this density matrix which is generally written as this density operator, which is dependent or function of time t. So this matrix element or this density operator, it can be defined as density of Mn, so that is equal to 1 over n. So that is for this one particle density operator, so k it is equal to 1 to n am of kth t into an star of kth t. So it is an ensemble average of this quantity am kt, that is the mth particle which is in the kth state, and this nth particle amplitude in this kth state, so which varies from member to member in this ensemble. Now if we have all these particles, they are identical and present in the same state, so then that is known as these diagonal matrix or diagonal elements. So that is density n into n, so that is equal to 1 over n summation of k is equal to 1 to n a n k of t square, so which is equal to 1. So a nth kt is itself a quantum mechanical ensemble average, so it is a double averaging process. So this equation of this density matrix, density of n and t, so we can write it as 1 over n summation of a n k t square, so which is equal to 1 for all k values. So what does it mean? So it means that the summation of all diagonal elements of this density matrix, so that is equal to 1 over n, 1 plus up to n times, so that is equal to 1 over n into n, that is equal to 1. So similarly density mn, so this we can derive. So the equation of motion for this density matrix, so it means that the equation motion, so that is the density function, it is varying with respect to time. So density of mn, So if I take the derivative of this equation, so with respect to time, so we need to find this value. So density of operator Mn, so that is equal to 1 over n summation of k, which is from 1 to n, am k of t into an k star into t. So taking the derivative of this equation, so this becomes curly density Mn over curly t. So that is 1 over n. So I will take the derivative one by one. So I can write this as an k star into t and take the derivative of this first function. So am dot k of t plus first function as it is, take the derivative of this second function a dot k star t. So putting the value of this am and ankt, so this equation becomes ih rho of mn t, so that is 1 over n into ih bar. So a n k t star, so this is equal to 1 over h summation of h of ml. So that is the Hermitian function for these two system m and l. So for this al k of t into an k star t. So this is the value of am dot kt. So that is if I consider that the system which is neighbor to this m system, that is the L system, and an kt star. So similarly using equation 3, so I can put the value of this. So this comes out to be, so since it is a antisymmetric wave function, so I will take this changes the sign. So here it is a negative sign. So this equation is 1 over 1h am k into t into summation of h nl star into al star into kt. So here what I have done is I have used this equation ih an dot k of t, that is equal to summation of h mn am k into t. So similarly the neighbor which is neighbor to n, that is the lth system. Now solving this equation, so what I get is ih rho of mn into t, that is equal to summation of Hermitian operator ml into 1 over n summation of alk into t an star k into t minus of 1 over n summation of amkt into al star kt into Hermitian, that is ln. So this h star nl, that we can write as h star nl, that is equal to h of ln with the sign. So solving this, so I can write this as ih density of Mn star into T, that is equal to summation of HML, and this is our density operator, so that is density of Ln. So this is first and this is Ln minus of summation density of Ml into H of Ln. So this we can write as operator H, operator rho, that is density operator for these two systems Mn minus of rho H for Mn. So this we can write as H operator density operator minus density operator H operator for this Mn. So this becomes IH density rho operator, that is equal to H operator rho operator. So when this commute, then the density, overall density of this whole ensemble, it is constant. So this equation, it is the quantum mechanical analogy of this classical Liebniz equation, so that we have derived in unit number 1. So this is quantum analogy of this Liebniz equation. So what does it mean? So if the given system is known to be in a state of equilibrium, then the corresponding ensemble must naturally be stationary. So what does it mean? So it means that the density of Mn, it should be equal to 0. So it tells us that, so what it tells us, that the density operator, so this equation, so it tells us that the density operator, so rho cap, it must be explicit function of this Hamiltonian operator H cap. So it should be explicit function of energy operator H cap, and the Hamiltonian, it must not depend explicitly on time. So second is this H cap, it must not depends on time. So if the basic functions phi n, so they are also the eigenfunction of this Hamiltonian itself, then these matrix of H and rho, it must be diagonal. So we can write this as H of phi n, that is equal to En into phi n. So where this energy, that is representing the energy eigenvalues, and phi n, that represents the eigenfunctions. So from this we can write down this H Hermitian operator for these two functions, phi of n, H of phi n. So this we can write phi n into En into phi of n. So En, so phi of n. So this we can write down as this delta of Mn. So this delta, that is generally known as the chronicle delta function. So therefore this Hermitian operator, so we can write down in terms of this chronicle delta function. So this expression, it is generally known as the energy representation of this symmetrical wave function. So similarly for this density function, so we can write down this density of Mn as rho of this second operator density n into this canonical delta function. So this is the density representation. So this is density representation, and this is the energy representation. So what does it mean that in the state of statistical equilibrium, the tendency of a physical system should be switched from one state to another state, and this must be counterbalanced by a equally strong tendency to switch between these same state, so in the reverse order. So from this we can find out the expectation values of this any physical operator. So before that there are some notations which I would like to tell you that so we generally write down these direct notations which we use for these quantum statistical derivation. So we write this phi n as n, so this is generally known as the cat operator, and phi of n originally say that, so this is our bra operator, and we write this phi of n as this delta of mn, or we generally write also this as delta of mn, or we can also directly write in terms of this mn. So for the identity operator h dot, that is equal to any operator which is acting on this physical parameter a. So this can be written as summation of phi n a cap into summation of phi m. So this term that is generally considered as this identity operator. So the expectation values of any physical quantity G, so it is when represented in terms of operator, so this we can write down as 1 over n summation of k, which varies from 1 to n, phi k star G operator into psi k into delta tau, where psi k t, so that is in terms of this amplitude am of k into phi of m, that is the states, and similarly psi star of kt, this can be written as summation of an k star into phi of n. So the value of this physical parameter operator g, so this becomes 1 over n summation of, so when I put the value of this phi k star and phi k, so this equation becomes summation of an k star phi n star g operator into summation of AMK phi m into d tau. So this becomes equal to 1 over n summation of k, which varies from 1 to n, summation of ANK star AMK into integration of phi n star into g into phi of m into d tau. So this is the Hermitian operator. So this becomes this is our density function rho of mn into g of nm. So this operator g, so this can be written as the representation in terms of rho operator and g operator. So that is generally known as the trace function of rho and g. So the maximum value of this g operator, it is equal to 1. So what does it mean? So it means that trace of rho into g, so that is trace of rho, the trace value, that is the sum of value of these density functions. And if function psi k, they were not normalized, then this operator g, so this can be written as the average value, so that I have already explained. So that is the trace of rho of g over the trace of this. So this trace that represents the sum of diagonal elements of these matrix. So this is the quantum statistics and the average value of this density operator or any other physical parameters which we want to represent in terms of this density and energy function. So this is all about for today's lecture. So in our next lecture we will discuss about the statistics of various ensemble, and then we will solve these some examples which are related with these microcanonical and canonical and grand canonical ensemble. So if you have any doubt, you can ask in the comment box. Till then, goodbye.